Hello everyone. In this video, we shall be discussing about an application that is text search. A common problem in the age of the web and the other online text repositories is the following. A given set of words, find all the documents that contain one or all the words. A search engine is popular example of this process. The search engine uses a particular technology called inverted indexes, where for each word appearing on the web, a list of all the places where that word occurs is stored. Machines with very large amounts of main memory keep the most common of these lists available, allowing many people to search for documents at once. Inverted index techniques do not make use of finite automata, but they also take very large amounts of time for crawlers to copy the web and set up the indexes. There were a number of related applications that are unsuited for inverted indexes, but there are good applications for automation based techniques. The characteristics that makes an application suitable for searches that use automata are the repository on which the search is conducted is rapidly changing. For example, Everyday News wants to search the day's online news articles for relevant topics. For example, a financial analyst might search for certain stock ticker symbols or names of the companies. Shopping robots want to search for current prices charged for the items that its clients requests. The robot will retrieve current catalog pages from the web and then search pages for words that suggest a price for particular item. The document to be searched cannot be catalogued. For example, Amazon.com does not make it easy for crawlers to find all the pages for all the books that the company sells. Rather, those pages are generated on the fly in response to queries. However, we could send a query for books on a certain topics, say finite automata, and then search the pages retrieved from certain words. Example excellent in a review portion. Let us discuss about non-deterministic finite automata for text search. Suppose we are given a set of words which we shall call the keywords and we want to find occurrence of any of these words. In applications such as these, a useful way to proceed is to design a non-deterministic finite automation which signals by entering an accepting state that has seen one of the keywords. The text of a document is fed one character at a time to this NFA, which then recognizes occurrences of the keywords in this text. There is a simple form to NFA that recognizes a set of keywords. There is a start state with the transition to itself on every input symbol. Example, every printable ASCII character if we are examining text. Intuitively, the start state represents a guess that we have not yet begun to see one of the keywords, even if we have seen some letters of one of those words. For each keywords, let's say A1 to uh, up to AK, there are case states, say Q1 to QK. There is a transition from the start state to Q1 on the symbol A1, a transition from Q1 to Q2 on symbol A2, and so on. The state Qk is an accepting state and indicates that the keyword A1, A2 up to AK has been found. Let us discuss one example. Suppose we want to design an NFA to recognize occurrences of the words web and eBay. The transition diagram for the NFA designed using the rules is shown in will be shown in this presentation. State 1 is the start state and we use sigma to stand for the set of all the printable ASCII characters. State 2 through 4 have the job of recognizing web, while states 5 through 8 recognize eBay. Of course, the NFA is not a program. We have two major choices for implementation of this NFA. Write a program that simulates this NFA by computing the set of states it is and after reading each input symbol. This simulation was suggested in the figure which we already discussed. Convert the NFA to an equivalent DFA using the subset construction, then simulate the DFA directly. This is the figure for an NFA that searches for the words web and eBay. Let us discuss about a DFA to recognize a set of keywords. We can apply the subset construction to any NFA. However, we can apply that construction to an NFA that was designed from a set of keywords. According to the strategy of previous section, we find that the number of states of a DFA is never greater than the number of states of the NFA. Since the worst case, the number of sets exponentiates as we go to the DFA. This observation is good news and explains why the method of designing an NFA for keywords and then constructing a DFA from it is used frequently. The rules for constructing the set of DFA is as follows. If Q0 is a start set and the NFA, then Q0 is one of the states of the DFA. Suppose P is one of the NFA states and it is reached from the start state along a path whose symbols are A1 to AM. Then one of the DFA states is the set of NFA states constituting of Q0 P. Every other state of NFA that is reachable from Q0 by following a path whose labels are a suffix of A1 to AM. That is any sequence of the symbols of the form AJ plus 1 and up to AM. This is general. There will be a DFA states for each NFA states P. However, in step B, two states are actually yield the same set of NFA states and thus become one state of the DFA. For example, if two states of keywords begin with the same letter, say A, then the two NFA states that are reached from Q0 by an arc labeled A will yield the same set of NFA states and thus get merged in the DFA. This figure is the conversion of NFA to DFA, and the link to this PDF will be given in the description. Thank you.